Welcome to Lecture 10. We're going to wrap up the Exam 2 material today, but what I'd like to do first is start off with exactly what we left off with in Lecture 9, and that is resonance. I realize that we probably need at least one more example for you to fully understand or just get a little bit more practice. So what we're going to work on first is ozone, the molecule ozone, which is O3. So what I'd like for you to do is do the Lewis dot structure. We'll practice with our geometry as well, and we will also talk about the resonance that this molecule exhibits. So if you want to stop the video and give all that a try and then come back, we're going to go ahead and do the Lewis dot. So oxygen, nonmetal, 6 valence electrons. So 3 times 6, this molecule has a total of 18 electrons. Obviously, it's all oxygens. Okay, connecting with dashes, step 2 on the Lewis dot steps. Give everyone 8. So this guy needs 6 more. The one in the middle needs 4 more because the 2 dashes are 4 electrons, 2 electrons per dash, and then the one on the end also needs 6. All right, so if we count these up, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, I have too many. Step 5 on the card says if you have these 5 elements and these 5 only, you may double bond. Okay, I have 2 oxygens, so I'm going to erase lone pairs from 2 of them, and that's where I'm going to put the double bond, because these oxygens that are on the second row of the periodic table cannot have more than 8 electrons around it. They only have the s and p orbitals available. So we've got 1 double bond, 2, 4, 6, 8, 10, 12, 14, 16, 18. So this is a good Lewis dot structure for this molecule. Let's talk about resonance first, and then we'll do the shape. This double bond can be here or here because these 2 atoms can also double bond. So that is an equivalent position. So in fact, we do have 2 resonance structures denoted by the double-sided arrow, and put the second one over, put the double bond over there, and then fill in with lone pairs depending on how many bonds. So I needed 6 here. This oxygen here, like the one up here in the middle, needs only 2 more because it has 6, 2, 4, 6, now 8, and then 4 additional on this oxygen here. So this molecule does exhibit resonance. Let's talk about its shape. Either structure is fine, they're both equivalent. So let's draw a circle around the central atom because that's the only one you are going to be looking at to determine shape. If I look at this central oxygen, I see 1 here, 2, 3. The double bond counts as a group. The steric number is 3. I have 2 bonding groups and 1 lone pair, so my electron pair geometry is not equal to my molecular. That is only true when there are no lone pairs on the central atom. My electron pair geometry is trigonal or triangular, trigonal planar because of steric number 3. Everything in the steric number 3 row on your geometry sheet has an electron pair geometry of trigonal planar. Everything in the steric number 4 has an electron pair geometry of tetrahedral, and so on. The molecular geometry for this steric number 3 with a lone pair is angular bent. All right, so we've done the Lewis dot structure, we've talked about the shape, and we have talked about the resonance of this molecule. Well, the last thing that we have to talk about in our Exam 2 material is polarity. So I know when I did the Lecture 7 live, I did not visit this link that I've cut and pasted from where that was with the notes for Lecture 7. Just didn't do it that day. We're going to go ahead and go there to remind you of the different kinds of bonding you can have depending on electronegativity. So get out the sheet that I gave you in Tuesday session with the electronegativity value. So it's a periodic table with electronegativity values in it because we're going to be using that. I really like this little analogy here. It's very cute, but I think it's very appropriate to understanding the differences between the different types of bonding. So let's go there. And it's about dogs. You know I like dogs. I like animals, all kinds of animals. Anyway, bonding by analogy, dog bones. So we've talked about ionic bonds in this material for exam 2. We've talked about covalent bonds. Now we need to make a distinction once again between pure covalent bonds, pure nonpolar covalent bonds, and polar covalent bonds, which we're going to talk about today. And then we haven't talked about metallic bonds, so this is a good opportunity to just go ahead and kind of look at that type of bonding. We really won't talk about it at all anymore in the course other than this little analogy. All right, as I mentioned before when we started this material on bonding, it is the electronegativity difference between the atoms in a bond that determines whether or not you are going to be ionic or covalent or polar. Ionic bonds, you've got one big greedy thief dog. That's why you always hear me talking about fluorine being the big dog on the table. Well, part of the reason why is because of this analogy. So you have a metal and a nonmetal. You can get a metal and a nonmetal that exhibits some covalent bonding. The going from pure nonpolar all the way to ionic, it's a continuum. It is not a line drawn in the sand. It just depends on how strongly the atoms are pulling on those electrons between them. So in ionic bonding, the metal loses electrons because it has the lower electronegativity. The nonmetal gains those electrons, and you end up with full positive charge on the metal, full negative charge on the nonmetal. And the bond is the force of attraction between the positive and negative, an electrostatic attraction between opposite charges. That is the bond. And it's a very strong one. That's why ionic compounds are all solids at room temperature. Then when you talk about sharing, you can have equal sharing, where the dogs are of equal strength or the atoms have exactly the same electronegativity, and you get that with any of your elements and so on, okay? Anytime you have exactly the same atom on either side, you've got pulling, the electronegativity is the same. So when you subtract the electronegativities, and that's what we're going to be doing. One is pulling, the other is pulling. It's the difference in the pulling that determines whether or not, one is going to take it and so on. And we're going to have some cutoffs for you so that you know whether you're going to call it covalent or ionic, or if you're going to call it polar or nonpolar. If you got a group full of chemists in the room, they would argue about where the line is between these two, between pure covalent bonding and polar covalent bonding. But for the sake of giving you something to work with, we are going to give you some cutoffs, okay? All right, so many chemists would argue, and I would be probably in that group, that unless you have exactly the same electronegativity, then it's not equal. All right, well, we are going to get to cases where it's not equal, and that is when we get a polar bond. So what happens here is the one that's pulling more, pulling on something negative. So remember, what we're talking about with this pulling is you're pulling negative electrons towards you. Up here in ionic bonding, you're pulling so hard that you actually take the electron away from the metal. In polar covalent bonding, they're still sharing, but the sharing is unequal. And the element or the dog that has the most electrons, the electrons that are being shared closest to it, develops a negative charge because they're pulling on negative things. The one that's losing this tug of war becomes slightly positive. So you will see these types of symbols used in your textbook. This guy gets a partial negative, and this guy gets a partial positive. It's a lowercase Greek delta. These are real measurable charges, not a full charge as in ionic, but depending on how unequal the sharing is, these bonds this polarity And magnets are often used as an analogy here, where you have a north pole and a south pole, although magnetism and electricity, while linked, are not the same thing. Anyway, they're measurable. I mean, you actually do have a positive end and a negative end. All right, so before we leave this, let me just say this once because I'm going to say it many times. Polarity in anything, in a molecule, in a substance, arises from the bonds. The unequalness has to occur in the bonds in order for it to be unequal. So it starts with the bonds. One quick introduction to metallic bonding. That's the last time we'll talk about it. Metals are different. You know that you can hammer metals into thin sheets and so on. You can pull metals into wires. You can't do that with any other substance. They also conduct electricity in the solid state. So in order to conduct electricity, you have to have moving charges. Well, the charges that are moving in metals are the electrons, the valence electrons. So the valence electrons go into a pool. I call this the communist view of bonding. So the valence electrons are shared equally by all of the atoms. So they go into a pool, which we also call a sea of electrons. That sea of electrons is in motion. So this is how it works. Let's talk about as if this, if this were sodium, for example. Each one of these dogs represents the sodium cation in A plus, and the valence electron, one per atom, is shared equally by all of the sodium cations. If it were calcium, then each of these dogs represents the calcium cation, which would be 2 plus, and the 2 electrons per calcium would be shared equally by the all of the cations, and so on. So in metals, the valence electrons move around continuously in motion. That's why they conduct electricity, okay? And that is why metals have very unique properties. That's why they conduct electricity so well, and so on. Heat as well. So very, very different type of bonding. All right, let's go back to the notes. All right, so we talked about ozone. I was hoping to get that back, but no. Let's talk about ozone in terms of electronegativity, because what we're about to excuse me, what we're about to discuss, like we just did with the bonding analogy, is whether or not you're going to have equal or unequal sharing. All right. All right. Just like in the H2 molecule, in the ozone molecule, you have exactly the same atom in both bonds. Okay, oxygen, 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 oxygen. So the electronegativity difference is 0. All right. So how do we know when to call it polar? Well, this is what we're going to use. And you can write this on the back of your card, because we're going to be writing a few more things on the back of that in just a moment. So if your electronegativity difference is between 0 and 0.4, we are going to call those bonds nonpolar covalent. Now these words polar and nonpolar only pertain to covalent bonds, where electrons are shared. If that electronegativity difference is between 0.5 and 2, we are going to call that polar. Now if you look at different textbooks, you'll see slight differences in this, but not much. It'll be like 0 to 0.5 or 0.5 to 1.9. Remember what I said, a room full of chemists would argue about this. And then anything greater than 2.0, we are going to call ionic. All right, so these are for you to be able to make a call between whether a bond is polar or nonpolar, or even ionic. All right, so a good example of a polar covalent bond is the oxygen-hydrogen bond in the water molecule. So let's put the water molecule up here, because we really haven't talked about the water molecule very much, because this is the time to talk about it, because water and all of its unique properties really exists because of the polarity of the water molecule. Okay, Lewis dot structure for water. We have 8 valence electrons, 2 for the hydrogens, 6 for the oxygen. So when I draw the Lewis dot, it's going to look like this. Okay? Geometry, steric number of 4 here on the central oxygen atom. And so if we look that up, we see that it is in the tetrahedral group. So its electron pair geometry is tetrahedral, but its molecular shape is bent. Now, I'm going to talk about the no's and yeses on the geometry sheet. Next to the bent picture on your geometry sheet, you see a yes written there. Okay? So let me tell you what the yeses and nos on the geometry sheet mean. Those yeses and nos are a direct answer to the question, is it polar? So before we go any further, what I'd like for you to do is, okay, I'm going to scroll. What I'd like for you to do is copy these to the back of your card. And I will draw the water molecule again right here. All right? All right. So we're going to talk about why that yes is there. And then we'll do lots of examples. Don't worry. All right, so step 1, 2, and 3. So you've drawn your Lewis dot. That's the front of the card. You have written your cutoffs for polarity on there as well, on the back. And now you are adding these 3 steps. So the first step in checking is what we're after here. The big picture is determining whether molecules are polar. Why is that important? Well, water would not behave the way it does if it weren't polar. It wouldn't dissolve salt and sugar and things like that if it were not polar. An example of something nonpolar is oil or gasoline. All right? You know they don't mix with water. Things that are alike tend to mix. So things with charges like salt and sugar, sugar's a polar molecule, dissolve in water. Water would not have the high boiling point it does if it were nonpolar. That high boiling point, that high specific heat, which we'll talk about later in the course, is because of its polar. But it's also why it keeps coastal areas like where we live so mild in climate. You go 50 miles up from the coast and the climate is different. Your gardening season is a little bit different, your last frost dates and so on. It's hotter up there than it is here in the summer. It's colder in the winter. The water that we live around acts as a heat sink, and the reason why is because of the nature of the water molecule. So that's why it's important. If we understand whether something is polar or nonpolar, there's so much that we automatically know about that substance. So that's the why. All right, so get your electronegativity sheet out, and we are going to look at the electronegativity difference between oxygen and hydrogen. Now, we are not going to multiply it by 2. We're just going to look at the one type of bond that is in this molecule. So I have to get my electronegativity sheet. All right, so I'm looking on that chart I gave you, and hydrogen has an electronegativity of 2.1, and oxygen has an electronegativity of 3.5. So this is what you're going to do. You're going to do 3.5 minus 2.1, okay? And that comes out to what? 1.4? No. 0.9 and 0.5. That's what I get. 1.4. Yeah, that works. 1.4. Okay. All right. You can use your calculator if you want to. 1.4 is solidly within the range of 0.5 to 2.0. All right. That's polar. So the bond for the water molecule is polar. All right. Step 2. If the bonds are nonpolar, stop. The molecule is nonpolar. All right. So that's not the case here. It would be the case in the ozone molecule where the bonds are nonpolar because the electronegativity difference is 0. 3.5 minus 3.5 is 0. So the ozone molecule, because the bonds aren't polar, is nonpolar. So it's very important to follow these steps because of this. let's say you did the Lewis dot structure for ozone, okay? We've already done it. We've already talked about its geometry. Now look on your geometry sheet for steric number 3, which is true for ozone, and the bent, geometry. I think I earlier labeled it angular bent instead of just bent. This is the first sheet I've seen that actually makes a distinction between the two bent geometries. But anyway, it says yes by both of them. So if you looked on the geometry sheet only, okay, and just kind of skipped steps 2 and 3, then you would get this wrong because it says yes by the bent geometry, which, remember, the yeses and nos are a direct answer to the question, is it polar? But as I said earlier when we were still on the dog bone analogy page, bonds, it is the polarity of the bonds that is going to determine whether the substance is polar. So this is nonpolar. That's why I have the steps the way they are. Check polarity of bonds. If it's nonpolar, you are not going to look at the geometry sheet. All right, that's true for ozone, not true for water. If the bonds are polar, check the geometry sheet to see if the geometry cancels out. All right, that's what it says just below here. I don't want to leave this because I want to talk a little bit more about it. Okay, so let's talk a little bit more about this polar bond business. First of all, I want to show you the way that your book draws it. So I'm going to draw the water molecule a little bit bigger down here. This polar bond is actually a vector. It has magnitude, it would be the magnitude part, and it has direction. So one way that we show that is with an arrow, okay, that points towards the element that has the higher electronegativity. And then we have this little positive tail on it, which means that this is going to be the positive end, the partial positive end of that polar bond. So it's a vector that has the length of the vector indicates its magnitude, and then the direction, of course, is the direction it's pointing in. So in the water molecule, you have two polar bonds, both pointing towards oxygen, which is why this end of the molecule is slightly negative, and this end of the molecule is slightly positive. This polar bond has what is called a dipole moment. That's kind of the formal name for the vector, all right? But I wanted to show you how it's depicted and what that means. And so what the yeses and nos on the geometry sheet are the result of vector, adding the vectors together, all right? And that's, that's a little higher level math than we're going to get into here. So that's already been done for you, all right, on the geometry sheet. So let's take one more example here before we get into the examples that are included in the notes, and that is carbon dioxide, all right? So we're going to do the Lewis dot structure, so front of the card, and then we're going to certainly look at its shape, and we're going to look at its polarity, okay? Because it is a good one to contrast with water. Two very common substances. All right, so valence electrons, 4 for carbon, plus 2 times 6 for oxygen. It's 12 and 4 is 16. All right, so carbon in the middle, bonds to oxygen. If I give everybody 8, don't stop at 16. It is too many. It's 20. So what that means is I'm going to have to put in some double bonds because these are two elements that can do that. If I put in one double bond, it's still too many. 2, 4, 6, 8, 10, 12, 14, 16, 18. So in fact, the carbon dioxide molecule has 2 double bonds, one on each side. Therefore, there is no resonance in this molecule because there's no place for this double bond to move to, these 2 double bonds. It's pretty much locked in place. All right, let's talk about the shape, and then we'll talk about the polarity. So if I look at this molecule and focus on the central atom, I see 2 bonding groups around the carbon. 2 big ones, but 2 bonding groups. That puts it in the steric number 2, which is linear. All right. Now, if you look on your geometry sheet, you see a no written for linear. Okay. But if the question were, is the bond polar in the carbon-oxygen molecule, that's step one, we need to look at our electronegativity difference, okay? So carbon has an electronegativity of 2.5, right? And oxygen has an electronegativity of 3.5. So 3.5 minus 2.5, you're always taking the largest minus the smallest. That gives you an electronegativity difference of 1. So this is a polar bond. And the dipole moment, the vector, is pointing towards the oxygens. Right? So equal in magnitude on either side, because it's carbon-oxygen, pointed in opposite directions. Well, if I have two vectors pointed in opposite directions of equal magnitude, this being the magnitude, they cancel each other out, and that is why the no is written there for linear. So if I had polar bonds, which is what I would do, I would go through my steps here. If the bonds are polar, check geometry sheet to see if the geometry cancels out. In this case, it does, and that no, again, is a direct answer to the question, is it polar? So let's talk a little bit about the properties of carbon dioxide versus those of water. First of all, from what we've learned, if I add up the molecular masses from the periodic table, the atomic masses, I get 18 for water, and I get 44 for carbon dioxide, 32 for the oxygens, I'm sorry, yes, right, 32 and 4, 44. Done it so many times. That's big, that's a pretty big difference. All right, but this is nonpolar, and this is polar. Carbon dioxide is a gas at room temperature. In fact, you can't even make carbon dioxide into a liquid or solid unless you really pressurize it. You know, dry ice, that is carbon dioxide as a solid. Carbon dioxide as a liquid is very hard to produce. And the reason why is because of this, right here, this. Water, by contrast, smaller, doesn't boil, doesn't become a gas until 100 degrees Celsius. It's because of the fact that this is a polar molecule. This one is not. All right. All right, we're going to scroll down and do the examples that came with the notes, and then we'll be wrapping up Lecture 10. All right, so let's talk a little bit about these caveats here with the steps. All right, so a no in the geometry means the geometry does cancel the polarity of the bonds. All right, I've already talked about that. The no's and yeses. So let me write it here. No and yes on geometry sheet, which you will have, but not for the final, is answer to question polar question mark. All right. Now, this is important. The yeses and nos are for molecules that all bonds are the same around the central atom. So that's what we've looked at. We've looked at carbon dioxide, where same around. Oxygen and hydrogen, same around the central atom. CF4, everything's the same. It's all carbon fluorine. So those nos and yeses are contingent on it being this case. However, if you end up with something like this, like CH3F, then you have carbon hydrogen, 3 carbon hydrogens, and a carbon fluorine. All right, where the electronegativity difference here between the carbons and hydrogens is 0.4. So right on it's nonpolar. Carbon fluorine, on the other hand, okay, is 4 minus 2.5, so it's 1.5. So there's no way that in the vector analysis of those dipole moments, of those polar bonds, that it's going to cancel out, even though next to the shape for this, which would be tetrahedral, it says no. That yeses and nos are contingent on everything being the same. If they're not the same, then it's going to be polar if you have a polar bond. All right? Okay, let's do some examples. Just leave this up. Determine, using the card and the geometry sheet, determine the polarity of HI, okay, and so on. All right? So, Quick little Lewis dots would probably be good at this point. All right, so we're going to do, I'm going to start them up here. So HI. Now, 2 atom molecules are not on the geometry sheet. Okay? So if the bond is polar, if bond is polar in a 2 atom molecule, the molecule is polar because you just got the one bond. And vice versa, if it's nonpolar, the molecule is nonpolar. Okay? So let's look at the electronegativity difference between hydrogen and iodine. Since I just have the one bond, 2.1 and 2.7. So the electronegativity difference here is 0.6. So the bond is polar, and this is a polar molecule. All right, that's what we're doing. Now, why do I have to do the Lewis dot? Well, I need to know what geometry group it's in, and if I leave out a lone pair or whatever on the central atom, then I can get the wrong geometry. So it is important to do the Lewis dot. All right, aluminum and bromine. You might think that it is a metal and a nonmetal, but the electronegativity difference is only 1.6. So, no. It is, hold on, 1.2. So the electronegativity difference between aluminum and bromine is only 1.2, which is going to make it, I told you that you're going to get examples. Aluminum is one of them because of how far over to the right it is on the periodic table, that you can get some covalent bonding. All right, so aluminum and bromine. Now aluminum is in the same group with, I'm going to do it over here, is in the same group with boron. So everything in that group is okay with 6. All right, so I've kind of skipped a step. Let's go back and count our valence electrons. So 3 for the aluminum plus 21 for the 3 bromines, group 7 times 3. So I should have 24 electrons here. Okay, give bromine 8, it wants 8, but aluminum's going to be fine with 6, like boron. All right. All right, so 6, 12, 18, 20, 22, 24. So focus on your, okay, we've already looked at the electronegativity difference, it's 1.2. So the bonds are polar. But the shape of this puts it in trigonal planar, or triangular planar. And next to triangular planar, it says no. There's no lone pair on the aluminum. So this is a nonpolar molecule, even though it has polar bonds. All right? So, Lewis dot structure first. Look at the electronegativity difference of the bonds. And if it's polar, you're going to need to look at the geometry sheet to see whether or not those polar bonds cancel out. All right? What I'd like to do, I'm running out of space, is erase at this point. So pause and copy if you need to. Use the big eraser. So I have a little bit more space. All right. Get rid of some of that. All right. Now, going back, SF2. All right, so SF2, we're going to do the Lewis dot structure first. So 6 plus 14 for the 2 fluorines, 2 times 7, that's 20. All right. SF, give everybody 8. And I'm guessing that because it involves fluorine, that the bonds will be polar, but 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this is a good Lewis dot structure. Electronegativity difference of the bonds, flipping the card over. 2.5 and 4.0, so the electronegativity difference is 1.5. So the bonds are polar. Now I need to look on the geometry sheet to see if they cancel out. Focus on the central atom. Steric number of 4. 2 bonding groups, 2 lone pairs. So it is in the tetrahedral electron pair geometry group, but the molecular shape of this one is angular bent. And it has a yes next to that geometry, which means that these Polar bonds do not cancel out. So yes, this is a polar molecule. When we are finished with this last example, I'm going to scroll. I want to go back to the geometry sheet and I want to talk about a couple of things that are written on there, okay, to make sure that you understand that. All right, one more. PCl5. 5 for phosphorus, 7 times 5, 35 for the chlorines, so 40. Phosphorus in the middle, surrounded by all those chlorines. It's going to give phosphorus what we call an expanded octet because it has 10 electrons around it, but that's okay. It's in the third row. Third row and below, remember, can have more than 8. All right. Now we're going to give each of these chlorines the lone pairs it needs. Each one needs to get a total of 8. And then we'll count our valence electrons to make sure we've done it right. So 6, 12, 18, 24, 30, 32, 34, 36, 38, 40. This is a good Lewis dot structure for phosphorus pentachloride. All right. Turning the card over, is the phosphorus chlorine bond polar? 2.2 and 3.0. So yes, it is, because 3.0 minus 2.2 is 0.8. And that puts it in the polar category. All right, so polar bonds. Polar bonds. Is the molecule polar? We have to check the geometry sheet. Now, you might have caught on already, some of you are smarties, that anything without a lone pair on the central atom is an automatic no. If you look at that column to the left, the ones that I call the pure geometries, you see no's on all of them. And that is going to be the case for this molecule as well, because it is triangular bipyramidal in its shape, and its electron pair geometry and its molecular geometry are the same because it has no lone pair, and it says no. So for this geometry, the vectors cancel out. So this is a non-polar molecule. All right, now I want to talk about the geometry sheet. I think what is going to go ahead and scroll. All right, so this is going to go away. Giving you a little pause there to stop it if you need to. And it's this, you know, what we just did is gone through here in a written discussion. All right. Okay. I want to go back to the geometry sheet, which is in a different, hold on, let me see if it's still here. Nope. I want to pull back up lecture 9, all right? And I want to talk about that geometry sheet just a little bit. All right, so there's some things written on it that, so I'm going to decrease my size here a little bit. Okay. The two things I want to talk about are, one, on your sheet, you have an extra geometry drawn in. My beautiful drawing. So you've got this drawn in because they left it off. It is possible in the steric number 5 to have 2 bonded groups and 3 lone pairs. Well, it just turns out that when you have that, the lone pairs occupy the axial positions, okay, here in the middle, and the 2 bonded pairs occupy these what's called the equatorial positions. This is an example when you have, so here's what type of molecule it would be. I3 minus is the example. So let's go through I3 minus. The lecture today is a little on the short side. So if I do I3 minus, 7 times 3 is 21, plus 1 for that charge, so 22 electrons. All right, iodine in the middle, iodine on either side, give everybody 8. All right, if I give everybody 8 and count them up, this is 20. So this central atom, because it is pretty far down on the periodic table, can take on an additional lone pair. So the steric number is 5, just like where it belongs on the table. Those 3 lone pairs occupy these positions here, which means that if the bonds were polar, which is not in this case, they would cancel out because it's almost like having a linear molecule. So this is an example of one, even though it doesn't pertain to this example. This is an example of a geometry where there are lone pairs on the central atom, but they cancel out, right? There's one more, and it's this one right here. There is a no next to this one, and it's for the opposite reason. The lone pairs, there are 2 lone pairs on this molecule, and 4 bonded groups, so the steric number is 6. Electron pair geometry is octahedral, but the shape is square planar. And because of the way that it arranges itself, if the bonds were polar, they would cancel out. So you need to be aware. In general, if there are lone pairs on the central atom, the polar bonds should cancel out if everything's the same. And that's certainly true for all of these other examples. But these 2 in particular right here that I've just talked about are exceptions to that. All right? Okay. Let's go back to lecture 10 and wrap this up. All right. So we've just got some few more examples to do, and then we're going to be finished. All right, arrange an order of increasing polarity. All right, so what we have here are 2 atom molecules. So what you're going to want to do is you're going to want to subtract the electronegativities. So 4.0 minus 2.1. So go ahead and pause and give that a try. And I'm just going to start writing what I'm writing up here is the difference in the electronegativities for the molecule. All right. So this little group of molecules is one that's used a lot in explanations of trends, because essentially what you're looking at here, since the fluorine, chlorine, bromine, and iodine are in the same family and in the same column, so essentially we know that electronegativity decreases as you go down the columns because atoms are getting larger, so they're opposite, okay? That's what you're seeing here. Fluorine's at the top of the column. It has the highest electronegativity on the table. And then chlorine's underneath it, and bromine and iodine. So you get a nice smooth trend here. So we just need to reverse the order. So increasing polarity means that HF will be at the end and HI will be at the beginning because it's the smallest. All right, and then HCl and HBr. All right, I believe it's not enough room there. All right, this next question, I've asked it on purpose because this is another way of asking which bond is the most polar. The way it's worded is, which bond has the highest degree of ionic character? Well, remember what I said, pure covalent is at one end of the spectrum, the continuum, and ionic is at the other. As you leave pure covalent, nonpolar, and you get polar in the middle, and you get increasingly polar, you're becoming more and more ionic. So you will see some books to look at electronegativity difference and talk about percentage of ionic character. It's the same thing as saying which is the most polar. All right. So if I look at this group of 3 here, and we're going to do the electronegativity differences. This one shouts out at me because I see a metal and a nonmetal. All right, which is going to most likely have the most ionic character. But let's go ahead and do the electronegativity differences. So hydrogen and sulfur, 2.5 minus 2.1, 0.4. Silicon and chlorine, 3.0 minus 1.9, so 1.1. And cesium and bromine, 2.8 minus 0.8, 2.0. Right, so cesium and bromine are, cesium's pretty far down on the alkali metals, so its electronegativity is pretty small. Bromine over there on in the halogens pretty large, so it's right on our cutoff for ionic. Right? Which of these molecules has the greatest polarity? Well, the polarity arises from the bonds. So one thing we want to avoid is you almost have to do the lowest dot structures. Because we could look at the electronegativity differences, and we will. But if I have two polar molecules, which I know there's a couple in here, then it's going to depend on the geometry as to whether or not it cancels out. So you almost have to do the lowest dots. So I'm going to go ahead and do those. All right. 6 plus 14 is 20. So a little quick one here. No double bonds because of the chlorine. Can't do that. I give everybody 8. That's a good lowest dot structure. Now, what I could do is look at the electronegativity differences first, and if the bonds aren't polar, then the molecule can't be polar. I could have done that. Sulfur and chlorine is 0.5, so the bonds are polar. Well, they're, yes, polar, yes. We said 0 to 0.4. And the geometry does not cancel it out, all right? Okay. PF3, are the bonds polar? Do I need to do the lowest dot? I would think with fluorine we'd have to. Yes, the 1.8 is the electronegativity difference. All right, so PF3. So does the geometry cancel it out? 5 plus 21 is 26. Fluorine, fluorine, fluorine. Give everybody 8. So automatically I see a lone pair on the central atom. So chances are the polarity is not going to cancel out. Okay? And in fact, this is 26. And this puts it in the triangular pyramidal group. Trigonal pyramidal, molecular shape, the electron pair geometry is tetrahedral, steric number of 4, but the molecular shape is trigonal pyramidal. And it says a yes next to that. So this one is quite polar. Much greater polarity in the bonds than in SCl2. Nitrogen chlorine, let's look at the electronegativity difference there. And in fact, the electronegativity difference between nitrogen and chlorine is 0. This molecule and this molecule, because nitrogen and phosphorus are in the same group and fluorine and chlorine are in the same group, are going to look exactly the same in terms of the lowest dot. Exactly. But the bonds aren't polar, so the molecule will be nonpolar for this one. So this is our biggest and most polar, our most polar molecule. All right? Okay. Let's do some quick, I'm going to do a little racing here. Let's do some quick lowest dots on a few, let's see, yes, we're going to need to, let's just go ahead and do the lowest dots, all right, because we're only at 48 minutes. We've got enough time. Because in A, I'm going to have an unequal around the central atom situation. So how do I know what's in the middle? Well, carbon is the right choice. I'd probably give you some guidance on that, but essentially it's the oxygen and the 2 hydrogens bonded to the carbon. You know, I've told you that it's the one farthest to the left. Well, hydrogen cannot be in the middle. It must be terminal. It must be on the end. And oxygen, if carbon's around and you got an oxygen, it's carbon that's going to take the middle position rather than oxygen. Okay. 2 plus 4 plus 6. This molecule has 12 valence electrons. The hydrogens are fine. That carbon wants 2 more, and the oxygen wants more. Now let's count up. 2, 4, 6, 8, 10, 12, 14. Too many. But I've got 2 elements from my list. Carbon, I'll tell, oh, I have the big eraser on. I'll tell you that carbon generally doesn't have lone pairs. There are a few examples where it does, but generally it doesn't like to have lone pairs. So the carbon-oxygen, I need to erase one more set of lone pairs on the oxygen, this is the Lewis dot structure for it. 12 valence electrons, 2, 4, 6, 8, 10, 12. So what I have here is, all right, so we've done the front of the card. Flip the card over. Let's check polarity of the bonds. Carbon and hydrogen, 0.4. But carbon and oxygen is 1.0. So what I have here is that unequal thing around the central atom. So no matter what the geometry sheet says, and the geometry for this molecule would be trigonal planar, steric number of 3 on that central atom, and it says no next to it. But that no is contingent on all the bonds around the central atom being the same. That is not the case here, so this molecule is polar. This is formaldehyde. All right, next, hydrogen peroxide. Remember, the hydrogens must be on the ends. So it's oxygen, oxygen, hydrogen, hydrogen. Okay. Number of valence electrons, 2 plus 12 is 14. The hydrogens are fine the way they are. Put in lone pairs on the oxygens. Now, what we have here are 2 central atoms, and we've talked about that. But let's check our electrons first. 2, 4, 6, 8, 10, 12, 14, so that's good. So I have this central atom here, and I have this central atom here. Okay? Well, in both of them, first of all, I have a steric number of 4. 1, 2, 3, 4. So the electron pair geometry is tetrahedral, but the shape is angular bent. And it says yes next to the geometry, but I have not checked the polarity of the bonds. Oxygen and hydrogen have an electronegativity difference of, we've done this one before, of 1.4 on one side. On this side, for this oxygen here, or this one here for that matter, the electronegativity difference is 0. So even though the geometry does say yes, this one is a yes because it's not the same. You have an unequal situation here. So they cannot cancel each other out. This is polar. All right. CF4. Got fluorine, so I'm guessing the bonds are polar. 4 plus 28 on the valence electron. 7 times 4 for the fluorine is 32. I put all the lone pairs in. There will be no double bond because fluorine's not one that can. Whoops, put those kind of close together. All right, so 6, 12, 18, 24, 26, 28, 30, 32. This is the good Lewis dot structure. Turn the card over. Carbon and fluorine. Electronegativity difference is 1.5, which makes the bonds polar. Is the molecule polar? Shape, steric number 4, no lone pairs. It is nonpolar. Tetrahedral geometry cancels them out. All right, one more. NO2. We got 5 plus 12. So for the first time, we have an unequal number of electrons, an uneven number of electrons. Doesn't really matter where you put the 7. Somebody's going to get 7. So let's go ahead and connect. Nitrogen in the middle. I'm going to give nitrogen 7, total of 7, 2, 4, 6, 7. I'm going to give each of these oxygens 8, and then we're going to count up. This is the only time you can have this situation, is when this number here is odd. 2, 4, 6, 8, 10, 12, 14, 16, 17, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18, 19. So I have 2 too many, and I do have 2 elements here that can double bond. So I'm going to erase lone pair off of each, and I'll put a double bond here. 2, 4, 6, 8, 10, 12, 14, 16, 17. Odd number of electrons. We have resonance here. One more time on the resonance. That double bond can move to that other position, which is equivalent. And I can draw my Lewis dot in a straight line. That's okay. All right. Now, nitrogen and oxygen. Turn the card over. Electronegativity difference is 0.5. So the bonds are polar. All right. If I look at my geometry around the central atom, a steric number of, technically it's a steric number of 3. 1, 2, 3. But I've got a electron on the, essentially a half of a lone pair on that central atom. So this one should take the bent geometry, and the molecule is polar. Now, you probably, in reality, that lone electron probably moves around to, to different atoms. It's going to be a reactive molecule. These molecules with an unpaired electron are called free radicals and are quite reactive. All right? That concludes what I call the whole enchilada in terms of looking at the properties, how we look at the properties of covalent compounds in particular. We spend more time on those because there's so much variety. All ionic compounds are solids, and all of your liquids and gases and biological tissues and so on and so forth, and plants and what have you are all covalently bonded substances. So we have to have a way of predicting their properties, and this is how we do it, through this method of looking at the structure and how equal the sharing is in the molecules. All right, that concludes Lecture 10 and Exam 2 material.